Can you see the slide?
Yes, ma'am.
Yes, ma'am.
So in the previous class, we discussed about the Compton effect and when photoelectric effect occurs and when the Compton effect occurs. Okay, photoelectric effect is when the photon interacts with tightly bound the electron which is associated with the atom. Okay, and Compton effect is observed in case of relatively free electron. Because a free electron, and thus what we say is a free electron cannot absorb a photon. Only bound electrons absorb the incident photon. That means the complete energy of the incident photon. uh, just we can prove it also that a free electron cannot absorb a photon. So let us consider that a photon collides with a free electron. It collides with a free electron. Now you can draw the small figure in which you are showing the photon, incident photon, okay, that is associated wave having, that is having an associated wave having frequency nu, and it interacts, or when it collides with the electron, what happens is, suppose the electron absorbs the complete energy and momentum, that electron will, that photon will vanish. Okay, so this is before collision. Are you able to hear me?
Yes, ma'am.
Yes, ma'am.
Yeah, so this is before the collision, so that photon having energy h nu is colliding with the electron, and then what we are considering is that electron absorbs the complete energy and momentum from the photon, and so it will move in this direction, forward direction. Okay, so this is the situation before collision and this is after collision. Now, according to the laws of conservation of energy and momentum, okay, according to the laws of conservation of energy and momentum, what we can write is the energy before collision is equal to the energy after the collision. The momentum before the collision is equal to the momentum after the collision. So before the collision means the energy of the photon is h nu, the energy of the electron is m naught c square. Okay, because it is a relativistic particle, we write it in this way. Okay, m naught is the rest mass, will be equal to, now it absorbing the energy from the photon and momentum from the photon, it will move. Okay, it will have the kinetic energy. So that energy is given by mc square. Okay, and according to the law of momentum, the momentum of the incident photon is h nu by c. Initially, the electron is at rest, so its momentum is 0. And after the collision, the momentum is p. So, from this particular equation, what we can write is this equation h nu is equal to pc. Okay. Now, from equation that we have already discussed earlier, okay, so this h nu plus m naught c square is equal to m into c square, but that can be written in this manner. Electron being a relativistic particle, okay, so we write the energy in this manner, square root of p square c square plus m naught square c raised to power 4. So h nu plus m naught c square is equal to square root of p square c square plus m naught square c raised to power 4. Now using this equation, h nu is equal to pc, that means equation number 2. We substitute for this PC, that is equal to h nu. So we get this equation as square root of h square nu square plus m naught square c raised to power 4. Squaring both these sides. Now, I hope that all of you are writing these things. Squaring both the sides, what we get is h square nu square. Let me squaring this one plus m naught square c raised to power 4 plus 2h nu m naught c square is equal to, squaring this means we will get h square nu square plus m naught square c raised to power 4. So these two terms are common on both the sides, so we ignore that. So what we get is 2 times h nu m naught c square is equal to 0. From this what we can say, this has to be either. Okay, that spelling is wrong. So either h nu is equal to 0 or m naught c square is equal to 0. Okay. So the two laws of conservation cannot be satisfied simultaneously. That means we started with an argument that the free electron completely absorbs the photon. Okay. But then after applying the laws of conservation of energy and momentum, we have arrived at this particular equation from which what we say is either h nu is equal to 0. That means the incident photon is not existing, or m naught c square is equal to 0. That means the electron is not there. Okay. So from this what we can say is free electron cannot absorb a photon. Okay. Write down these things. Here the spelling is AITHER. Okay. So write down this thing, and when you complete that, I hope you have written that, or I will give 2 minutes for this. When you complete that, please let me know. Please let me know when you complete that.
Yes, ma'am.
Have you completed?
Yes, ma'am.
Okay, so now we have completed the black body radiation, photoelectric effect, and Compton effect. Okay, one point I missed while explaining to you. Okay. Now, this is the equation that you get for mm, Compton shift. Okay. And already we have discussed so much about that the delta lambda depends only on the angle phi. It is independent of the nature of the material which is scattering the X-rays. It is independent of the wavelength of the incident X-rays also. Okay. Now, one small point I would like to mention here, that the Compton effect is not observable by visible light. Okay. It is observable only with X-rays. Now, here to understand that or to explain that, what we can argue is, suppose we irradiate, if we instead of X-rays, suppose we consider some monochromatic beam of light. It is in the visible spectrum, so around 5000 angstrom is the wavelength. Okay. Now that light, when it is made incident on the light element, those photons will also get scattered. Okay. But what happens is, the shift that is obtained, it is irrespective of the incident wavelength. So what is the maximum possible shift that can be obtained in Compton effect? If somebody remembers or somebody has written, can you tell me how much is the maximum possible shift? किसी को याद है? Okay, when that shift is maximum, at what angle phi?
180 degree.
180 degree. How much it is? Yes, how much it is? H upon m naught c is constant and phi is 180. तो कितना?
H upon m naught c.
2 times h upon m naught c. Now, what is the value of h upon m naught c? It is 0.02426. Okay, we will go to that. I thought you will remember. Okay, so this is 0.02426 and it is maximum at 180 degrees for and that value is 0.04852. Now, this much is the shift. So, this shift is significant if it is the X-ray that is used. But if it is the visible light, then this shift is negligible corresponding to that incident light. Okay, I'll repeat again. So, if the X-rays are used, then this shift is maximum for whatever incident radiation is there, whether it is X-rays or it is visible light. Okay, maximum possible shift obtained is this much. So this shift is significant if you consider the incident beam to be of X-rays. Because what is generally what wavelength we consider for X-rays? Can anybody guess? कितनी रहती है? Obviously, with the help of some tube, we produce the X-rays and we can change it. Okay, but generally, what is the wavelength? It is very, very less. Energy content is more. कितनी रहती है wavelength? Around around 1 angstrom. Okay, all of you, I don't know why you are not ready to speak out. Okay. 1 angstrom incident wavelength है, तो 0.04852 angstrom is significant. But when you are considering the visible light, that wavelength is around 5000 angstrom, so this shift is negligibly small corresponding to the incident wavelength. Okay, it's not that the shift doesn't occur. Shift will occur, but that is negligibly small. So what we can say is it is not observable. That means for detection purpose, if we make the use meter for incident and the scattered beam, then the shift is not detectable. Okay. So now we have completed the black body radiation, photoelectric effect, and Compton effect. So now we can go for the numericals, because separately we don't get time for the tutorials in this timetable. So there are 4 classes, so we can make use intermittently some time from some class for the numerical. So just wait, I will first take up the numericals on photoelectric effect. Okay, so I will share that. Can you see the slide?
Yes, ma'am.
Okay, so this is the first numerical. Determine the frequency, wavelength, and energy in joules associated with a photon of energy 2.4 electron volt. Simple. Okay, so these are some very simple numericals first, and then some based directly on the photoelectric effect. Okay, so you can write down this in short, okay, and then we will solve it. Determine the frequency, wavelength, and energy in joules associated with a photon of energy 2.4 electron volts. The value of H, that is Planck's constant, is given 6.63 into 10 raised to the power minus 34 joules second. And C is already 3 into 10 raised to the power 8 meters per second. Okay. So how do we solve it? Simply E is equal to H nu. Okay. E is equal to H nu. We have to find out the frequency, so nu is equal to E upon H. Then energy is given in electron volt, but we know the conversion. 1 electron volt is equal to 1.602 into 10 raised to the power minus 19 joules. So the energy of the photon is given, it is 2.4 electron volt. So it is in joules, it is 3.84 into 10 raised to the power minus 19 joules. So that E in joules will be 3.84 into 10 raised to the power minus 19 joules. Okay. So energy in joules. So how many parameters we have to determine? Frequency, wavelength, and energy. So energy in joules is this one. So one answer is this. Then E by H. Okay. Energy is put here divided by value of H. It is 5.8 into 10 raised to the power 14 hertz. Okay. And wavelength. E is equal to H nu means it is Hc upon lambda. So it comes out to be 5173 angstrom. Once you complete this, actually it is a very simple numerical. Okay. Once you complete writing, just let me know. We will proceed to the second one. Roll number 19 is there. Ayush. Roll number 19 is there. Roll number 13 is there. Anand. Roll number 13. Yogesh, sorry. Roll number 13. Roll number 72 is there. Anil. Roll number 83. BK Sharma. Okay. Have you completed?
Yes, ma'am.
Yes,
Okay.
ma'am.
Now we will proceed to the second one. Determine photon energy corresponding to X-rays of wavelength 1.3 angstrom. Express it in electron volts. E is equal to h nu or hc upon lambda. Okay. Now, if you have to find it out in electron volts, then you have to use the proper conversion. So first you can find out by using these values of H and C, you get it in joules, then convert it into electron volts. E is Hc upon lambda. Now individually such small numerical will not be asked, but then in some numerical it may be required to be determined. So put the value of H 6.63 into 10 raised to the power minus 34 joule second. C is 3 into 10 raised to the power 8 meters per second divided by wavelength is given 1.3. Angstrom means 10 raised to the power minus 10 meters. So it comes out to be, now you calculate it. Okay. With the help of calculators, you also calculate that and you tell me whether you are getting the same value or not. Okay. But that value comes in joules because you have put this in joule second and meter per second. So you get it in joules. To convert it into electron volts, you multiply it by 6.242 into 10 raised to the power 18 electron volts. So you get the answer to be 9.55 kilo electron volts.
Ma'am, we can't use that 12500 divided by 1.3.
Can. First check whether this is correct or not.
Yes, ma'am, this is correct.
This also you can use. If the wavelength is given in angstrom, then you can find out the energy in electron volts by using this relation also. 12,400 divided by, but directly you have to put the value of wavelength in angstrom. That means if it is given in other unit like nanometer, then you have to convert it. Okay. And put this value of lambda only, which is having unit angstrom. But there is a small difference that arises. So this is also not a very lengthy method. So you can directly use the constants and also find out. Okay. So that is about the second numerical. Now the third one. Can anybody read? Anyone who can come forward? कोई एक जन
Yes,
read
ma'am.
हाँ, बोलो.
A source is emitting 100 watt of green light at 5000 Armstrong. How many photons are emerging from source per second?
Yes. Now that numerical is to be solved. Okay. Yeah. So the energy emitted in time t is given by this power into time. Okay. Power is given 100 watt and that is 100 joules per second. Okay, that power is energy per time. So that is given. So we can find out the energy. 100 joules per second multiplied by. Now what we have to find out? How many photons are emerging from source per second. Okay. So this T is 1 second. So 100 joule per second into 1 second. That is the energy emitted in 1 second. Okay. Now number of photons emitted per second will be that N will be, because we know that E is equal to NH nu. Total energy emitted per second is E, that is equal to NH nu. So N will be E upon H nu, that is E into lambda upon Hc. E is 100 joules. Lambda is 5000 angstrom. So 5000 into 10 raised to power minus 10 meters divided by H 6.63 into 10 raised to power minus 34 joule second multiplied by C is 3 into 10 raised to power 8 meters per second. If we solve this, what we get is 25.14 into 10 raised to power 19 photons per second. So like this, whatever numerical is given, using the basic equations and the basic knowledge we have regarding that E is equal to H nu corresponding to 1 photon and total energy is E is equal to NH nu, we can solve any type of numerical. So once you complete writing that, you will let me know. Complete one? Have you completed?
Yes, ma'am.
Okay. Now who will read the next one? Okay. I'll tell. Roll number 90, Anisha.
Ma'am, may I?
Roll number 90. Shrishti. Roll number 91.
Ma'am, may I?
What is your number?
I'm 37.
Whatever number I am calling, those students are absent. So let me mark them absent. So is it Swaroop?
Ma'am, Naman,
Roll number
37.
37. Okay, Naman, you are the CR of this class, no?
Yes, ma'am.
There are only 85 students who are present today. And whatever number I am calling, those are absent. Whether they have just joined for the sake of joining or they are really absent. It's difficult to make out. Okay, Naman, you can read.
The
Naman?
photoelectric threshold wavelength of tungsten is 2730 angstrom. Determine maximum kinetic energy of electrons ejected from tungsten by UV light of wavelength 1800 angstrom.
Correct. I just wanted someone of you to read so that only it's not that I should speak, no? Okay, so now we have to solve this. Now what is given is the photoelectric threshold wavelength of tungsten. That means lambda 0. Okay. From lambda 0, what you will be able to find out?
Work function.
Correct. Okay. So you have to determine the maximum kinetic energy of electrons ejected. Wavelength, incident wavelength is given 1800 angstrom. So we will be using this equation. Maximum kinetic energy is equal to E minus W0. Okay. So E we can find out by this formula 12,400 upon how much is the value of wavelength of incident light? It is 1800 in angstrom minus Hc upon lambda 0. It's a simple numerical. You calculate it and you will get it as 2.35 electron volts. Now check whether you also get the same value, that is 2.35 electron volts. I have given the answer.
Same value is coming out.
Same value, no?
Yes, ma'am.
Yeah. So I don't think it requires more than 2 minutes to write. हो गया है सबका लिखना?
Yes,
Yes,
ma'am.
ma'am. हो गया.
Okay. Next. Yeah, this is the fifth numerical now. Anyone can come forward?
Ma'am, can I read?
Yes. Number?
When roll number 30. Sri Hari Deshpande.
Sri Hari Deshpande. Okay.
When UV light of wavelength 2540 angstrom falls upon a copper surface, the retarding potential necessary to stop the photoelectrons is 0.59 volt. What is the photoelectric threshold wavelength of copper?
Yes. So, thank you for reading it for me. When UV light of wavelength 2540 angstrom, that means the incident wavelength is given. Okay. Then the retarding potential necessary to stop the photoelectrons means what is given? Can anybody guess?
Stopping potential.
Correct. So either you write it as V0, V0 or Vs, whatever it is, that is given. Okay. And what is to be determined is the threshold wavelength of copper. So whenever you have to solve the numerical, first you have to gather whatever is given and then you can use the equations. So kinetic energy maximum is given by E into Vs. Okay. Now these are all the equations that we have derived. E into Vs is equal to kinetic energy maximum is also given by h nu minus h nu 0. So Hc upon lambda minus Hc upon lambda 0. Okay. What you have to find out is the threshold wavelength. That means lambda 0 is to be determined. So from this particular equation, rearranging the terms, what you get is Hc upon lambda 0 is equal to Hc upon lambda minus E into Vs. So lambda 0 will be equal to, if you rearrange again the terms, then lambda 0 will be equal to Hc upon this whole in the denominator. Hc you can take always as 12,400. Okay. And here it is 12,400 divided by, again this wavelength in angstrom is 2,540 minus, how much is this E into Vs? Because this is when it is in electron volts. So here this voltage is 0.59 volts. That means E into Vs will be obviously 0.59 electron volts. Okay. Stopping potential is 0.59 volts. That means E into Vs will be 0.59 electron volts. Okay. So you get it to be 2890 angstrom. Okay. So tell me when you complete that.
Ma'am.
Completed?
Yes, ma'am.
Yes, ma'am.
Yes. Now we will go to the numerical number 6. Yes, anybody? हाँ मुझे नंबर बताओ अपना.
39.
34. ठीक है 34. क्या है आपका नाम?
अंकित कुमार ठाकुर.
ओके.
UV light of 1800 angstrom irradiates tungsten cathode which has a threshold of 2300 angstrom. Calculate first maximum kinetic energy of emitted photoelectrons. Second, work function of tantalum.
Correct. Thanks. Okay. So what is given is a wavelength of incident UV light, that is 1800 angstrom. What else? The cathode is made up of tungsten and its threshold, wavelength is 2300 angstrom. What you have to find out is maximum kinetic energy of the emitted photoelectrons and also the work function of tantalum. Okay. Actually, threshold wavelength is given directly and work function is to be determined. So we'll go to the solution of 6th. Okay. So work function and the threshold wavelength are directly related by this relation. W0 is equal to Hc upon lambda 0. So this you put as 12,400 and lambda 0 is 2,300 in angstrom, whatever is the value that we have written. So whatever value we get, we can attach electron volts with that. So it is 5.39 electron volts. Are you able to hear me?
Yes, ma'am.
Yes, ma'am.
And maximum kinetic energy, it's very simple, that h nu minus h nu 0, you put the values. Okay. 12,400 corresponding to Hc is taken out. So 1 upon 1800 minus 1 upon 2300, whatever value you get, that is 1.5 and unit is electron volts. Let me know when you complete that.
Same answer is coming.
Yeah. Okay. So shall we move to the next numerical?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, the 7th one. Yes, anybody?
May I, ma'am?
Yes, number?
52, ma'am.
What is the
Photocell
name?
operates with
Just a minute. Just a minute. Atharva.
yes, ma'am.
Now you can read.
Photocell operates with visible light. The work function of tantalum is 4.2 electron volt. barium is 2.5 electron volt and lithium is 2.3 electron volt. Which of these materials can give rise to photoelectric effect?
Yes, thank you. So what is given is the photocell is operating in the visible light. That means what type of light is made is incident? It is in the visible range. That means visible spectrum. Okay, and the different materials which are given are tantalum, barium, and lithium. Tantalum having a work function of 4.2 electron volts. Barium is having work function of 2.5 electron volts, and lithium is having a work function of 2.3. Now, out of these three materials, which we have to find out which materials will give rise to the photoelectric effect in this visible spectrum. So what we do is we consider the extremes. Okay, that means the lambda corresponding to the visible range is it is from 4000 to 7000. Okay, so if it is 4000, then we find out the value, that is 3.1 electron volt. That means the threshold corresponding to the threshold. Okay, what is the work function for which this light can give rise to photoelectric effect? So it comes out to be 12,400 upon 4000. So it is 3.1 electron volt. Okay, if it is at the other end, that means 7000, then if the work function is 1.77 electron volt, then it can give rise to photoelectric effect. And all the wavelengths in between that, for those the
Ma'am, all
threshold,
between this range.
yeah, between 1.77 to 3.1. Okay, all can give rise to photoelectric effect. So now what is given is tantalum is 4.2. 4.2 is out of this range. Barium is 2.5. Yes, it is within this range. Lithium is 2.3. It is also within this range. So what we can conclude from that, barium and lithium will give rise to photoelectric effect with visible light, but not tantalum. Okay, because the work function for tantalum is high, whereas
Ma'am?
wavelength, yes,
Ma'am, whose work function is less than 1.77 also gives, na?
no. What you want to say for these materials? What is the
No,
requirement?
ma'am, I am talking general. Whose work function less than 1.77 also give na photoelectric effect.
Yes, yes, but we are talking about these three materials, whether with visible light, these three materials will give rise to photoelectric effect. Okay. So in the visible, if the incident light is in the visible range and these three materials are there, which are irradiated, then out of these three, which will give rise to photoelectric effect. Okay. Have you followed?
Yes, ma'am.
Yeah. So it is when we say the statement itself of photoelectric effect is when metal is irradiated with light of suitable wavelength. That means when I say tantalum, then that that radiation should have the wavelength, okay, which should be less than this, not in the visible range. Okay, then only it can give rise to photoelectric effect with tantalum. Have you understood?
Ma'am.
So that is about the numericals on photoelectric effect. You can even try to solve more numericals from some standard books if they are available. Okay, but generally this is the way in which the numericals will be asked. Now some time is left, so I think we should go for some numericals on Compton effect. What do you say?
Okay, ma'am.
Yeah, because this is over. Now I will stop sharing this. You just wait. Yes.
Ma'am,
Huh?
can you please show the second numerical again?
This one? Second means this one, no? Yes, who is it?
Yes, ma'am. Yes, ma'am.
So you have some doubt or you have to write it?
Ma'am, actually, when you were showing the solution, some network issue was there, and my
Okay,
screen
write
was
down
just
quickly.
ready.
Okay.
Okay.
Or you can take the photograph.
Yeah, ma'am. Sure. Done, ma'am.
Okay. Yes, can you see?
Yes, ma'am.
Yes, only 3 numericals are there. Whether it will be possible to complete that or we will do it in the next class, please give your opinion quickly.
Next class, ma'am.
And we can do first one.
Yes, we can do first one.
इतना immediately response next class किसने बोला? Just I would like to know. कौन है वो? Yes. Who responded so quickly?
Hi, ma'am.
What is your name? Roll number?
X077.
77. शुभम, क्यों क्या हुआ बेटा?
Sorry, ma'am.
अरे नहीं सॉरी क्या है उसमें? कौन सा क्लास है इसके बाद?
Yes, ma'am.
Communication
skills.
ऐसे ही है वो तो।
हाँ क्या है?
नमन बोल रहा है मैम, नमन। मैंने मैम नमन।
नमन
मैं कंप्लीट फर्स्ट क्वेश्चन मैम।
नमन आई वांट टू टॉक टू यू। क्या बोला आपने? ऐसे ही है?
सॉरी मैम। मैम आई वांट टू से दैट
ऐसा
वी
क्या
कैन टेक
बोल?
फर्स्ट क्वेश्चन मैम।
और नहीं कैसा है कि वंस यू स्टार्ट इंटरैक्टिंग नो आई लाइक दैट, लेकिन ये क्या है ऐसे ही है यानी क्या मतलब है? कौन पढ़ाता है?
मैम जयपाल सर।
ओके, एक न्यूमेरिकल करते हैं। नमन पढ़ो।
Yes, ma'am. X-rays with wavelength 1 angstrom are incident on a carbon block. The scattered radiation is viewed at 90 degree to incident beam. Determine the wavelength of scattered X-rays.
Okay. Can you tell me what is the equation for finding delta lambda? Can anybody tell me what is the expression for finding out delta lambda?
Delta lambda is equal to lambda
H upon M not C.
theta.
H upon M naught C 1 minus cos phi. And how much is the value of H upon M naught C? It is 0.02426 angstrom. Okay. Simple question is there. Incident wavelength is given. Angle phi is given. You have to find out wavelength of scattered X-rays means lambda dash. So lambda dash minus lambda is equal to delta lambda. Once you find out delta lambda, then add it to the wavelength lambda. You get that. Okay. Such simple and easy numerical will not be asked in the exam. Even if it is asked, it may be for 1 mark or coupled with that something else will be there. हो गया complete?
Yes, ma'am.
ठीक है. So we will stop here.
No.
Okay. And in the next class, I think today is Wednesday, no? Friday, next class. Our next class is on Friday.
Yes, ma'am.
That is a holiday this time.
Holiday.
Yeah.
Yes, ma'am.
So we will meet on, I think
Next week.
Saturday. I think Saturday we have a class. Okay.
ma'am.
So thank you very much for joining.
Thank you, ma'am.
Have a good day.
Thank you,
Thank you,
ma'am.
ma'am.
Thank you, ma'am. Have a good day too.